Yeah, and no, this can be erased. So I'm gonna. Okay, so today I want to tell you about the measure of duration and distances in cosmology, and this is actually one of the first things you would learn if you take a cosmology class. And it might appear simple at first, but it's actually quite subtle. So let me start from the beginning. What is cosmology? Cosmology is about trying to describe, to understand the evolution of the universe, the evolution of its contents, understand its history. And to do that, we need to observe the universe. Typically, we want to talk about things that are far away, and so you cannot go there and make experiments. Okay? So if you want to observe them, something had to travel from this point to us. And in most cases, the thing that traveled from there to here is light. So now we also have observation of gravitational waves and neutrinos, but this is more marginal, so I'm only going to consider that. The typical setting of cosmological observation can be represented with a sketch here. We are on Earth, and we are receiving light signals from, for example, this source 1 or this source 2. And I'm saying that these are far objects, and the question will be, how do you tell they are far objects? How can you measure their distance? But to give you an order of magnitude, we're talking about things that are at least 10 to the power 20 kilometers away. So it's hard to comprehend how far that is. And because these objects are far, and because the speed of light is finite, it takes time for this light to travel to us. So when we receive it, this light has been emitted a long time ago, and we see the object as it was a long time ago. And by long time, I mean something of the order of at least 100 million years. Very far, very, very long time ago. Okay, but again, my question today would be basically, how can you get this estimate? By just looking at the light that you receive from these objects. And that will lead me very quickly to discuss the phenomenon of expansion of the universe. And the last thing that I will try to get to is to discuss how you can prove that space is expanding and how can you measure this expansion. But let me start with this first. So how do we measure distance in cosmology? Typically, because we look at an object again very far, what we will use are references. We need some reference. So we will look at an object and we will be able to measure this distance, for example, if we know its luminosity, which is, for example, the luminosity is the amount of energy it emits per unit area, per unit time. So an object that has a luminosity that we can recognize because it belongs to a standard class of objects that by looking at them and measuring some properties, we can tell what their luminosity are called standard candles. There's some reference. So let's say you know the luminosity of this object. So this object is going to emit, let's say it's located here, our source. It's emitting light isotropically, and so this light is spreading. This energy is spreading. It's spreading in an increasingly larger sphere. And when this light is reaching us here on Earth, the radius of this sphere is going to be the distance between the Earth and the source. I'm going to call that the L, the luminosity distance. So then, if you look at the luminosity that you have here, well, the area over which the energy has spread is given by the sphere. So the area of the sphere is 4 pi, this distance squared. So the luminosity that we measure is the intrinsic luminosity that we can compute divided by this quantity. So by comparing what we measure and the luminosity we know of the object, we can infer the luminosity distance. That's the first way of getting the distance of an object in cosmology. A second way would be to use as a reference the size of the object. Let's say you have an object and you know it belongs to a category whose size you can estimate by just looking at it. We will call that a standard ruler. And let's say we know the size of this object to be, sorry, this is a gamma. So let's say we know the size of the object to be gamma. Then you can compare what you know the size of the object to be with the solid angle with which you see this object in the sky. And by simple trigonometry, you can relate this known size of the object, gamma, with the angle of theta with which you see it and the distance at which it is, that here I'm calling dA, the angular distance. Okay, so is that it? So that's two ways of measuring the distance, and you could say, okay, well, now we know. But actually, it's not that easy, because in general, dA, and so the luminosity and the angular distance will give you different results. If you look far away enough, and you use these two methods that seems like a reasonable way of estimating the distance of your object, they will give different results. And the reason why they will give different results is because your universe is not static, it is expanding. Okay, so why is the universe expanding? How can we understand that? To put it simply, let's say it's the consequence of relativity. Relativity tells you that measure of time and distances depends on the environment. They are not absolute, and they depend on the environment around you. And typically for a universe, the universe is evolving, the content of the universe is changing, and so your measure of distance is changing. For a universe that is isotropic and homogeneous, it's actually quite easy. It's changing in the following way. So let's look again at Earth and a source there, and let's say they are at rest. So you can define what is called a co-moving set of coordinates, in which, in this case, their distance that we call the co-moving distance, chi, is going to be a constant. Okay? But actually, the distance that makes sense physically, that, for example, photons will see, is called the physical distance. And it's related to the co-moving distance by a quantity here, A of t, that is called the scale factor. So these distances are altered by this factor, and they are altered in a time-dependent way, despite this object being fixed in the co-moving coordinates. Okay, and the precise way this A of t, this scale factor, evolves will depend, okay, so depends on time, but it also depends on the content of the universe. So it will depend, for example, what percentage of the matter in the universe is in the form of radiation, so photons and neutrinos, what percentage of the matter in the universe will be in the form of baryons, which is basically, in cosmology, what we call baryons is basically anything that looks like ordinary matters, for example, hydrogen, and maybe other forms of matter. So this relation, you can compute it from the Friedman equation, but I'm not going to do it here. Just know that the universe is expanding, this distance is changing, and it depends on the way it does, depends on the content of the universe. The only thing that I need to know for now is that the universe is expanding, not contracting. So as a function of time, A is growing. So here I've plotted, it's just a drawing, okay? It's not a realistic drawing. There's no scale. I've plotted A, the scale factor, as a function of time. So it's an increasing, always increasing function of time. And here I'm denoting T0, the time today. I'm going to take as reference for this high-dimensional number that today the scale factor is going to be 1. And in the past, it was less than 1 because the universe is expanding. Okay? So this is measuring, in a sense, how much smaller was the universe before in the past at a certain times t, for example. Let's say this is t, and then that gives me the value of the scale. Okay. So the universe is expanding, but how does that change the picture for my measure of distances? So let me discuss how that changes how signals emission and reception occur in an expanding universe. First, let's look. So we are in a situation again where we have Earth here and a source there. And this source is going to emit two signals. It's going to emit a first signal at a time t, and then a bit after, just a bit after, a second signal at time t plus dt. These signals travel towards Earth, and when they are received on Earth, they are going to be received, let's say, today, so at t0, and slightly later time, t0 plus delta t prime. And the key point is that here, at reception, the second signal arrives with the time delta t prime that is longer than delta t. And it's quite easy to understand why. When the second signal was emitted, the universe had expanded a bit more. So the second signal covered more physical distance than this one. And so it's the time duration between the two signals has increased. And you can show that delta t prime over delta t is equal to 1 over the scale factor at emission time. And so because I said that I normalize the scale factor to be 1 today, this is larger than 1. Which means that there is a dilation of duration. The duration of a phenomenon at emission will be longer at reception. Okay. And conversely, if we look at the rate of something, the frequency of something, the frequency is going to be shorter. So if the frequency of a process is nu at emission, at reception it's going to be smaller, and it's going to be nu0 over, so this quantity that I've renamed 1 plus z here, So it's going to be mu over 1 plus. An important fact is that this applies, for example, to light. So let's say you send light in the visible spectrum that is rather blue. When this light is received, its frequency will have been reduced, and so it will have get redshifted. It's going to look redder than when it was sent. This frequency has decreased, and that's why we call this factor Z the redshift factor. It tells you how much light that was sent at this time got redder as it traveled to us. Okay, so with that aspect, let me review this discussion of how we measure distances of objects in cosmology, and let me look again at the luminosity distance. So we know the luminosity of a source here. It's emitting a certain amount of energy over a certain area and during a certain duration delta t. And all of these aspects are actually going to be affected by the expansion of space. First, the energy. So the energy of a photon is equal to the Planck constant h times the frequency of this photon. So let's say it sends a photon with an energy that is h nu. This photon travels to us, but its energy is going to be decreased because frequency is decreased. So here, the energy is decreased by this factor 1 over 1 plus. So the energy is decreased, but in addition, the energy is spreading out, just as it did before. It's spreading out over an increasingly larger area, and when it reaches Earth here, it's going to be spread over a physical distance. The radius of the sphere in physical distance is going to be the scale factor at arrival, so today 1 times the co-moving distance. And so the area of the sphere is going to be 4 pi squared. Finally, you send this amount of light was sent over during a certain duration delta t at emission, and the time over which we were going to receive it is dilated. So we're going to receive the same amount of energy, the same energy, the same photons are going to be received over a longer amount of time by 1 plus. So if you put all of this together and you put that in the same form as here, which is the protocol that we use to extract the distances, we compare the received luminosity compared to the one we know, then you will find that the DL that you estimate with this procedure is given by 1 plus z times the co-moving distance. Okay? Now, I'm not going to do it for the angular distance, but you can do the same kind of reasoning, and you'll find that, for example, this gamma here is going to be stretched by the scale factor of emission. And then what you will find is that the angular distance on the other end is going to be the co-moving distance chi over 1 plus z. And so you see that these two things are indeed, as advertised at the beginning, they're different. So indeed, if you do the same procedure described here, you will find different distances for sources that are different. Now let's say you want to compute the co-moving distance chi here. None of this measure gives you access to the co-moving distance. If you want to compute it, you need, in addition, to extract the redshift of the source. So this, we need to compute this to get the co-moving distance. How do we do that? Again, looking at the light of a source, and this light, as we see, got fainter as it travels, but it also got redshift. So let's say you know the spectrum of your source. You know the amplitude of each frequency of light it's sending to you. So let's say here, I'm plotting in orange the spectrum that you expect to see from the source. So this is the frequency, the amplitude as a function of the frequency in the light of the source. And in particular, let's say because you look at a star or a galaxy, you know that certain frequencies are not going to get to you because they will be absorbed by the atmosphere of the star or the composition of the galaxy. So you have this pattern here in orange where you have almost a continuous spectrum, but sometimes you have absorption. And you know what elements are going to absorb, so you know where, at which frequency you should see this line. For example, you should see a line here at noon. But then you observe your object, and you see what's in white here. What you see in white is that you have the same pattern of absorption line, but it's shifted toward shorter frequencies. Shifted towards the red, and so you can compare the position where you expect this absorption line nu to the one where you measure it at, which is mu0. And by doing this comparison and using this formula for the redshift, you can directly, by comparing these two numbers, get the redshift of the source. And when getting the redshift of the source, if you know its luminosity distance, for example, you can also compute its co-moving distance. Okay? So this answered this question. Now, very briefly, because these two things are very tied together, how do you get the emission time at which this light was emitted? Well, actually, Z is directly giving you the scale factor at emission, A of t. And I was telling you here that A of t is a monotonically growing function of time. So for each value of the scale factor, you have a corresponding value of time. So you can directly use Z as a timestamp. Instead of saying it was emitted at this time, you can say it was emitted at this redshift. For example, the source that has a redshift of 1 here, you can compute that this source emitted when the scale factor was 1/2, which means that the universe was twice smaller than today when this light was emitted. Now, if you want to convert this timestamp of redshift in years, you have to know this function. You have to know A of t, which means that you have to know the content of your universe. You have to know how much there is of each type of matter. And so this number of years is a model-dependent statement, of course. And when you see numbers in years, in general, it's assuming the standard model of cosmology and the values that we've measured to the best of years. Okay, to end that, let me just show you how you can try to prove the expansion of space and how it was first done. So, as I was saying, there's a correlation. If you see an object on Earth, here you see an object on Earth, and two objects that were at the same distance and send their light and you receive their light at the same moment must have emitted the light at the same time, because the speed of light is the same in every direction. So it means that there is a correlation between the time of emission and the distance at which are these objects. And because the time of emission is correlated to Z, the redshift, there's a correlation between the redshift and the co-moving distance of its object, and so between the redshift and the luminosity distance of its object. And this is interesting because these are two things that you can measure independently. And the fact that there's a correlation between the distance of its object and how much redder you see the light that you receive, this is a prediction of the expansion of spacetime. There's no reason it will be the case. This will not be the case in a static spacetime. So in general, again, unfortunately, this relation depends on your model. You find that DL is a certain function of the redshift, but also on the content of the universe. So I'm not going to give it to you here. But you can expand. You can say, okay, I'm going to look at small redshift, so things that are close by. Things that it's infinitely close by, so at 0, there is no distance, this is 0. So redshift 0 would correspond to emission today, so something that is near us, DL is 0. So the first term in the Taylor expansion is going to be proportional to Z. Then you have other term, and I'm going to name the coefficient H0 minus. So what this predicts is that there's a linear relation between the redshift of the source and its luminosity distance. So what you can do is measure many sources and plot both their luminosity distance as a function of their redshift. And if you do so here, you will hope to find a linear relation. And that's what you found, and that's what Hubble did sketchily somehow in 1929. And before him, Lemaitre did it also in 1927. So this linear relation between the luminosity distance and the redshift is known as the Hubble-Lemaitre law, and it's a proof of the expansion of space because it validates the prediction of the expansion of space. Okay, to end, you can also measure the rate of this expansion just by getting the slope, because the slope of this is giving you H0 minus, it's giving you H0, and H0 is actually the time derivative of the scale factor over the scale factor at 2 days time, so it's the rate of expansion. And you can expand this plot to try to measure how the rate change if you go to larger redshift. And that's actually still what is done today. For example, that's the kind of thing that the DAISY experiment is doing today. We had a talk about this a few months back. So although this is something that was done 100 years ago, it's still very much relevant in today's cosmology. So thank you for your attention.
Okay, thank you very much. So, any questions from experts? Yeah.
I have a very naive question. So I don't know what expansion of the universe really means. If objects move from each other with speed, and there are two related phenomena that happen. One is that might be non-uniform, so depending on where the universe is located, the rate of expansion is different. And the other thing that might happen is that objects just happen to move with their own speed. They're not stationary. So how do we first of all, how do we know that the expansion is uniform or close to uniform? And how do we, like looking at a specific object, how do we know that this rate that we computed only caused by the expansion of the universe, but not also by the object moving away from us with some?
Yeah, okay, very good question. So my answer would be the following. And again, not at all an expert on that. But so first, the universe is not completely homogeneous. It's only a first approximation that it's homogeneous. And the scale that I quoted at the beginning are scales where the universe starts to look homogeneous. If you look at the solar system, it's not homogeneous. There's some planet somewhere, there's some void somewhere. If you look at the galaxy, it's not homogeneous. You have to look at groups of galaxies over some distances to get something homogeneous. So it's an average statement, and in general, the universe is not homogeneous. So you could say the rate of expansion or the rate of change of distances is not homogeneous. Second, so that's the first statement, but there's on average an expansion. So what you can do is look at this plot, for example, and you could decide, so sorry, maybe let me say it, and maybe someone will correct me, but when you see an object and you see a redshift, you cannot tell if this redshift comes from the fact that this object is moving away from you because there's a particular distance, or because it's dragged by what's called the Hubble slope, which is the expansion space. But what you can do, though, is that if you have a tendency, you can decide that, okay, the rate of expansion is given by this tendency, and the deviation from this tendency gives you the peculiar velocity of the object. And one example would be, for example, the closest galaxy that we have to the Milky Way is Andromeda. And you can compute what will be the redshift of this galaxy, and it would be something positive. It would be, I think I computed yesterday, something 10 to the minus 4. And so it's very small, but it's positive. But actually, when you do measurement, the galaxy is going towards, or two galaxies are colliding. And this is a peculiar velocity. It's not obvious. That's all it's.
Any comment? Two. The second question in particular relates quite subtle notions about how is the structure of space or space-time really a physical thing? How much is it to do with let's say logical assumptions and on point against that same hypothesis that this was an actual logical conventionality. And the way that this is kind of the idea is that motion, certain types of motions will have physical. They're driven by forces, the physical interactions, and we have an idea of what those kind of interactions might be. And any motions that cannot be attributed to those direct forces somehow must either come from the nature of inertial frames that you've got. So this is where the logical assumptions are, which is spend some time on. In ordinary classical mechanics, one of the basic assumptions is that you're picking out a special class of inertial frames which are homogeneous and isotropic, that these are now locally homogeneous and isotropic in a different way from the universe system of large scale, which is an average thing. And it's not clear that those assumptions in classical mechanics really hold in GR, but locally, if they're on small enough scales, they should. And so there's this interplay which makes that second question ridiculous. Yeah, thank you, Christy. Do you want to say something?
No, I think no, I don't think so.
Okay.
It's almost not like building micro efficiency. Like we should assume the spectrum of other field like over time. It's actually is the cognitive constant of the field, right?
Sorry.
Like the red bottom, your right.
Yes.
So I'm just wondering why we don't believe the coupling constant not change over the path of
So you're asking about the variation of fundamental constants?
Yeah.
Yeah, okay. So I don't know about this. I think there are constraints on that, no, coming from early universe and in particular coming from way before these galaxies were formed. Typically, this would be spectrum of galaxies or supernovae or things like this. And then we have constraint that dates back to before the formation of this object, that would be deep blank nucleosynthesis. And I guess from that we can get some constraint on the variation of fundamental constant. So we believe we know the value of fundamental constant at this time, which is what we can see into a spectrum. That'd be my answer. Nice. Again, I'm not.
People have considered that kind of thing, and so far there is no like evidence, concrete evidence that those constants have been changing over time. This is another thing. People have said that not only time but also spatial dependence. No, so
Yeah. A very naive question. So this expansion rate, what kind of magnitude are we talking about? Because for what you say, measurements done maybe last year of objects are useless now. And after that, what is the distance that we can expect to have an effect, a significant effect of this expansion? As you say, short distances, there's no effect, but at what distance can you expect?
Okay, thanks. So you can infer the constant here, and that gives you the rate of expansion. And this rate is going to be expressed usually. So I'm going to give you the value in the units that's given in cosmology in general, weird units. So the measure that we have right now, okay, so there's a conflict on the exact value of the rate, so the rate of expansion. That's called the Hubble tension. It's a big problem in cosmology at the moment. One way to compute it is to do just this. The other is to do an early universe measurement, then you get different results. So I'm going to give you roughly an order of magnitude because that doesn't matter. So let's say that this constant, which is the rate of expansion, is equal to 70 kilometers per second per megaparsec. That's where the weirdness comes. It's megaparsec. Check. That means that if you take an object, let's assume that this is correct. Let's assume, so if you take an object that is, it's not megaparsec, is it? Can someone correct me? They know the value of the Hubble constant. It's correct?
Okay, minus 42 GeV.
You're kidding. So this is good. So if you look at a galaxy that is located, an object that is located at 1 megaparsec away from Earth, this is going to fly away from us at 70 kilometers per second.
I think the bigger issue is what's the megaparsec.
Yes, I know. I'm getting to that, Christian. So a parsec is roughly, I have it here because of course I don't know it. Okay, 1 megaparsec is directly 30 times 10 to the power 18 kilometers, but that maybe doesn't speak to you. But to give it in light year, this is, do I have it here? Okay, I think it's 3 times 26, so it's 3 million light years. So it means that this looks like it's fast, but it's only fast when you have something that is very far away, so millions of light years. But if you have something that is very close, this needs to be suppressed. So 1 light year away, this will be suppressed by 10 to the minus 90. That's the kind of distance we're talking about. That's what I was mentioning, like 10 to the power 20. And plus there is the question of when you get to smaller scale, how much is the expansion actually relevant, because you can, okay, that's very subtle, but let's say, anyway, scale of the galaxy, scale of the existence of humanity, even if you're optimistic, which I'm not, this is not relevant.
Okay.
before in time, I think you are a bit
No,
expert.
another question.
Okay, so
Now, a question about the Hubble constant.
Yes.
How accurately do you know the Hubble constant? Constant, well, how small time independent?
Okay, so it's not constant. That's the first answer. And the way you can see that is by expanding this. This is a first order expansion. You can go to next order and you get something like this. That's the customary way of doing it. And this Q0 parameter is called the deceleration parameter. It tells you how much the universe expansion is decelerating. Okay. And it's funny because it's called the deceleration parameter because everyone was expecting that the expansion was slowing down, because this is what happened if you only put, for example, radiation and baryons in your universe. Turns out the expansion is accelerating. So Q is negative and H is increasing. Okay? And the way we know that is by, so this was the first order statement, you get something linear, then you push it and you get something that curves off. Okay, this is how you can measure it, for instance.
okay. So any questions from anybody? Yes.
So do we have experts? Sorry, I'm not an expert. Is there like any conjecture, any understanding about what the function A should look like?
Oh yeah. There's an exact form.
There's an exact form.
Yes. So yes, you can solve it. I can give you the equation where you can. Yeah. So you can solve it in general. It's just differential equations. But yeah, you can get it. So you have to solve the Friedmann equation, but so basically you have that h squared. So a dot over a is equal to 8 by g3, and the sum of all types of matter in the universe, the density of all types of matter in the universe. Checking that out. Okay, there's a c squared. And then you can invert that to get a of t as a function of time. So once you know all these things dilute, you can get a of t. So for example, if your universe was full, if it's full of, is it radiation? Radiation, then it's 2/3, I don't remember. It's maybe 2/3 when it's radiation, or maybe it's matter. But anyway, it's a power, it's a certain power when you have only radiation or matter. Once you know that, then you can find the relation between D, L, and Z. Okay, it's just a matter of finding the redshift and inverting. So yes, you know the formula. And that's actually, to go even further, let's say you have a parameterized version of this, and that's what people do. You can check this parameterization against your measurement, and that gives you, by just plotting this line, that gives you a prediction for each parameter. How much of this there should be, how much of that there should be. That's what actually, like, even modern experiments.
Maybe you can mention the Hubble tension program.
Yeah. So
the most important cosmological program.
well, is it? Okay, so again, someone asking me how much do we know H0, how closely do we know it? We know it very precisely, but in two different ways that disagree. We have two different ways of precisely measuring something in disagreement. So this is called the Hubble tension. And again, so I think Derek and Rio would know more about this than I will. But the idea is that you can, it depends on how you do it, but it's maybe a 5 or 5 sigma tension on the value of Hubble, depending on how you look at it. Some measurements, so the linear measurement would give you H0. I'm going to write it. Okay, by 4. You have some people that will tell you H0 is around, I think, 65, and some people will tell you it's more around 70. And this groups in two types of measurement. There are measurements that are building this diagram, so looking rather at so in cosmology terms, it's like late universe or more recent stuff. Then you get this larger value. And there are people that are doing things differently. They are looking at as far as we can, which is looking at the first light of the universe, the cosmic microwave background. And by understanding the difference between all this, by looking at this cosmic microwave background, it's fluctuating, it's the way that it's anisotropic, you can infer another value in these inputs. And both are very well measured, and they disagree, and we don't really know why. Not gonna lie, people that believe this value based on the cosmic microwave background, because it just directly measure light and infer something, have strong suspicion about this value, and everyone's saying, okay, but to get this value, you have to measure many, many different objects. And to know the distance of an object that is very far, actually, you have to know the distance of an object that is closer and take a reference from it. So there's a lot of things, there's a lot of astrophysics that comes into play. You have to be sure that when you say, for example, that you know very well the luminosity of an object without measuring it, you have to be sure that you actually know the object well. And okay, maybe it's difficult, but people did a lot of work and they still find this value. So it could also be that actually there is something we don't understand this model, that we have to change the model. We have to change the function H. And and actually, okay, if you even more like the universe, as I said, is accelerating, and for the longest time we thought that we could explain the acceleration by introducing some type of matter known as dark energy that would give you an accelerated expansion. And this was given in the form of something that you may have heard, it's called lambda, the cosmological constant. And recently, that's the result of DAISY, it seems that maybe even this already, we don't know what is dark energy, but we know how to parameterize it. That was the idea. And even now, we don't really know what would be the right way of parameterizing it in our question. So 100 years later, still a lot of questions.
Yeah, okay, thank you. Yeah, so do you have any future perspective?
No, no, that's too far from where.
Okay. Okay, questions? What? That okay, question from online participants? Okay, okay, so thank you very much. So next Friday I'm absent, so I want to ask you a favor. Anybody will volunteers to chair this meeting? Is there